The oldest black holes in the universe might not have come from dying stars at all. They might have formed in the first fraction of a second after the Big Bang, born directly from the chaos of the early cosmos. These are primordial black holes, and they represent one of physics' most intriguing mysteries. In the earliest moments after the Big Bang, the universe was incomprehensibly dense and filled with violent fluctuations. In some regions, if enough matter concentrated in a small volume, it could have collapsed directly into a black hole without waiting for a star to die first. These primordial black holes could have been microscopic, smaller than an atom, yet weighing as much as a mountain. Others might have been planet-sized in mass, but no bigger than a grain of sand. Some scientists believe primordial black holes could account for dark matter, the invisible substance that comprises most of the universe's mass. If they exist, they'd be nearly invisible to us, detectable only through their gravitational effects. Detecting one would connect us directly to the Big Bang itself. Now we enter territory where black holes stop being theory and become something we can actually detect. Stellar mass black holes form when massive stars, at least 20 times heavier than our Sun, run out of fuel and collapse catastrophically. When nuclear fusion shuts down, gravity takes over completely. The core implodes in less than a second. Atoms crush. Protons and electrons merge into neutrons. If the star is massive enough, even neutrons can't survive. Everything compresses into a singularity, creating a black hole weighing 5 to 50 times what our Sun does, squeezed into a space no larger than a city. We find stellar black holes by watching what they devour. Many exist in binary systems, paired with normal companion stars. As the black hole pulls in gas from its companion, material spirals inward at extreme speeds, heating to millions of degrees and glowing in X-rays. This is how we discovered Cygnus X1, one of the first confirmed in the 1960s. More recently, gravitational wave detectors like LIGO have caught signals from stellar black holes merging. When two collide, they create ripples in spacetime itself. The 2015 LIGO detection was historic. Two stellar black holes collided over 1 billion light-years away and released more energy in that fraction of a second than all the stars in the observable universe combined. Millions of stellar mass black holes drift silently through the Milky Way right now, many dormant and invisible. For decades, astronomers faced a puzzle. We found small black holes, and we found giants, but nothing in between. This gap led to one of astronomy's greatest mysteries. Where were the intermediate mass black holes? They range from roughly 100 solar masses to 100,000, sitting squarely between stellar and supermassive types. They should exist. The math supported it, but evidence was frustratingly scarce. That changed when gravitational wave detectors began recording black hole mergers with unusual masses. Some collisions involved objects clearly in the intermediate range, too big to be stellar mass and too small to be supermassive. We also found hints in dense star clusters like Omega Centauri, where a black hole weighing about 8,200 times our Sun appears to reside. The leading theory is that they form in crowded star clusters where collisions happen frequently. A black hole consumes a star. Another black hole joins it. They snowball, growing quietly over millions of years through repeated mergers. Why does this matter? Intermediate mass black holes might be the missing bridge between stellar and supermassive types. They could be the seeds that eventually grow into the billion solar mass monsters anchoring galaxies. Each discovery rewrites what we think we know about how black holes grow. At the center of nearly every large galaxy sits something that defies comprehension: a supermassive black hole. These aren't millions of times heavier than the Sun, they're billions. Sagittarius A star, at the heart of our Milky Way, weighs about 4 million solar masses. Our entire solar system orbits this monster, but Sagittarius A star is tame compared to others. The supermassive black hole in M87, at the center of the Virgo cluster, weighs 6.5 billion solar masses. Its event horizon is larger than our entire solar system. In 2019, the Event Horizon Telescope gave us the first direct image of a black hole, the shadow of M87, a dark circle surrounded by glowing gas. That image confirmed what we'd suspected but never directly seen. Supermassive black holes are real, they're enormous, and they're actively feeding. When they consume material, they become quasars, some of the brightest objects in the universe, outshining entire galaxies of stars combined. Their jets extend for millions of light years, sculpting the space around them. Here's the puzzle. We're finding them in the early universe, just a few 100 million years after the Big Bang. They shouldn't exist yet. Growing to 1 billion solar masses should take billions of years. but we're seeing them when the universe was less than 1 billion years old. Something is wrong with how we understand their formation. The truth is, we don't know yet, and that mystery is driving current research. Most black holes in the universe aren't sitting still, they're spinning, often at tremendous speeds. This rotation fundamentally changes how they interact with spacetime. When a black hole spins, it doesn't just rotate like a planet or star. It literally drags spacetime around with it in a phenomenon called frame dragging. Spacetime flows in the direction of the black hole's rotation like a cosmic whirlpool. This creates a special region called the ergosphere, a zone outside the event horizon where the effects of spin become extreme. Inside the ergosphere, standing still relative to a distant observer becomes physically impossible. You're forced to move, forced to orbit in the direction of the black hole's rotation. You can still escape if you're fast enough, but you have to fight against the flow of spacetime itself. Here's what makes spinning black holes truly remarkable. In principle, you can extract energy from them. This is called the Penrose process. If you drop an object into the ergosphere and split it at precisely the right moment, one piece falls into the black hole, while the other escapes with more energy than the original object had. The energy difference comes directly from the black hole's rotation. In theory, an advanced civilization could use spinning black holes as cosmic power plants, tapping into their rotational energy. It's completely valid according to Einstein's equations. When two black holes get caught in each other's gravity, they begin to spiral inward in a slow, deadly dance that can last millions of years. But when they finally collide, the impact is so powerful, it literally shakes the fabric of spacetime. These collisions create bursts of energy known as gravitational waves, ripples in spacetime itself. You can't see them with your eyes, but instruments like LIGO and Virgo can detect these ripples as they pass through Earth, and we've caught them repeatedly. In 2015, scientists made history by detecting the first gravitational wave signal from a black hole merger. Two stellar mass black holes collided, and the signal lasted just a fraction of a second. In that blink, they released more energy than all the stars in the universe combined. Since then, dozens more collisions have been detected. Some involve black holes bigger than we thought possible. Others revealed unexpected behavior like highly tilted spins or weird masses that don't fit any category. When two invisible monsters come together and become one, the universe roars. The ripples from that collision carry more energy than seems possible, traveling across the cosmos for millions of years. Theoretically, if two supermassive black holes collided, the gravitational waves would be so massive they'd reshape reality across billions of light years. We haven't caught one of those yet, but we're listening. We've reached the frontier where established physics ends and speculation begins. Charged black holes, or Reissner-Nordstrom black holes, exist in theory where electric charge persists on the black hole. In principle, they'd have multiple event horizons layered like an onion, but large charges rarely survive in space. More speculative still are white holes, the theoretical opposite of black holes, where everything must escape and nothing can enter. Some physicists propose that white holes connect to black holes through wormholes, creating shortcuts across the universe. Then there's the truly strange: naked singularities, exposed points of infinite density without an event horizon. If they exist, the laws of physics themselves would break down in their presence. There's also the possibility of micro-black holes, subatomic objects potentially created in particle accelerators, like the Large Hadron Collider. They'd evaporate almost instantly through Hawking radiation. But detecting one would prove that extra dimensions exist. Some theorists propose that what we call black holes might not be black holes at all. Objects like boson stars could mimic black hole behavior without having a singularity. That would mean everything we've assumed about event horizons could be fundamentally wrong. Level 7 is where our understanding reaches its limit. These objects may or may not be real, but they show us how much we still don't know about black holes and the nature of spacetime. At the heart of every black hole lies a singularity, where physics breaks down completely. General relativity predicts it exists. Quantum mechanics says it can't. There's also the information paradox. When a black hole evaporates through Hawking radiation, does information about what fell in disappear forever, violating quantum mechanics, or is it preserved in ways we don't yet understand? Physicists propose solutions like information encoded on the event horizon, but no one has proven it. We're also finding supermassive black holes far too large to exist early in cosmic history, and LIGO keeps detecting mergers with unexpected properties. Each discovery forces physicists to update their models and acknowledge how much remains unknown. Solving black hole mysteries might not just tell us about gravity. It could reveal the fundamental nature of time, information, and existence itself. Black holes are where science stops giving answers and starts raising even deeper questions. They're not just cosmic monsters, they're clues to the true nature of reality itself. If you enjoyed exploring these 7 levels of black holes, be sure to like and subscribe so you never miss our next deep space breakdown. And if you're ready for more mind-bending cosmic danger, check out our video, The Most Lethal Things in Space Explained in Detail, a tour of the universe's most destructive forces, from killer stars to galaxy-shredding phenomena.